Hey everyone! In this video, we're going to talk about some concepts and tips for solving 2D motion and vector problems, and then we'll walk through and solve some different types of problems. Pause the video at the beginning of each problem and try solving it first. When you're done, or if you can't figure it out, watch the video to see how to work through the problem and check your answer. So, what are some of the concepts and skills that we need for 2D motion and vector problems? First, we need to know some geometry. We use triangles a lot, especially right triangles, so we need to know how to find the side lengths and angles using the Pythagorean theorem and the right triangle trig functions, sine, cosine, and tangent. We should also be familiar with finding different angles in sets of triangles or parallel lines. And it's not as common, but circular motion is two-dimensional motion, so we might need to know some geometry about circles. Next, we need to be familiar with coordinate systems. We usually use a Cartesian coordinate system, and we label the axes as x and y, each with a positive and negative direction. For some problems, we need to work with axes that are rotated or even flipped. We also need to know how to use coordinates to describe the position of a point or an object within a coordinate system. Next, we definitely need to know how to work with vectors. We should be able to at least roughly draw a vector when given its magnitude and angle. We should also be familiar with the different ways that a vector's angle can be described relative to other axes or directions. We need to know how to find the components of a vector and how to find its magnitude and angle. And we also need to know how to add vectors, either graphically by using the tip-to-tail method, or mathematically by adding their components. Finally, we need to be familiar with the one-dimensional kinematic equations. We might be working with an object in two-dimensional motion, but we're going to be answering questions about its motion, either in the direction it's moving if it's a straight line, or we're going to find the x and y components and use the 1D kinematic equations for each direction. Those are some of the key concepts and skills that we need, and you can go back and review anything you're not familiar with. Now let's cover some tips for solving these types of problems. Tip number 1, always draw a picture. You should always draw a picture at the start of a physics problem, but it's especially helpful and sometimes necessary for 2D motion and vectors. Draw things big enough to fit everything that you want to include. Use a picture as a helpful reference, but remember that it may not be accurate. Unless you use a ruler and a protractor, your vectors and angles probably won't be accurate. For example, if we're given the magnitudes and angles of vectors A and B, and asked to find their resultant vector C, the vectors we draw might not be accurate enough to show us if C points in the positive or negative x direction. So it's always good to draw things out, but trust the math instead of your picture. Draw the x and y axes if it's useful for the problem, but it's not always necessary. Keeping track of your directions and signs is important, but if the problem is simple enough, you don't always have to apply the x and y axes to the situation. And remember that when we draw vectors, they can be moved around. So even if a vector is attached to an object, you can draw the vector at the origin to see its angle relative to the x and y axes. Tip number 2, know the different ways to describe angles. Pay attention to the wording around angles and make sure you understand exactly which angle is being given or which angle you're being asked to find. Use the conventional angle, where positive angles are counterclockwise from the positive x-axis, in these cases. If you're just working with a vector and it's not related to a physical scenario, especially if there's no units, if the angle is relative to the positive x-axis, or if the angle you're given is greater than 90 degrees. But in most other cases, when in doubt, just use a positive reference angle. That usually just means a positive angle inside a vector's right triangle relative to the x-axis or the horizontal. Also, make sure your calculator is set to degrees instead of radians if that's what you're working with. And tip number 3, turn a 2D problem into a 1D problem. If you're given, or you're starting with, a 2D vector, and you're asked about the motion in the x or y direction, or the horizontal or vertical direction, then you can find the components of the vector and use the 1D kinematic equations for each direction. Or you can start with two 1D motion components and use them to find a 2D vector. Remember, there's no 2D kinematic equations, there's only a combination of 1D kinematic equations. Alright, now let's solve some problems. Vector A has a magnitude of 15 and an angle of 122 degrees. Vector B has a magnitude of 23 and an angle of 46 degrees. What is the magnitude and angle of the resultant vector of A plus B? Let's read through this again and find the important information. We're given two vectors. Vector A has a magnitude of 15, but we're not given any units. It has an angle of 122 degrees. So let's write down A equals 15 and theta A is 122 degrees. Vector B has a magnitude of 23 and an angle of 46 degrees, and we'll write that down. The problem is asking us to add vectors A and B and find the magnitude and angle of the resultant vector. Let's call the resultant vector C so it's easier to keep track of, and write down that we're trying to find C and its angle theta C. Next, let's draw these vectors to get an idea of what we're trying to find. The problem didn't give us any length units, and we're told vector A has an angle greater than 90 degrees. That should tell us that these angles are probably measured counterclockwise from the positive x-axis, which is the conventional way to describe angles using a single value. So let's draw vectors A and B starting at the origin of the x and y axes. Vector A has an angle of 122 degrees from the positive x-axis, and we'll label the magnitude as 15. Vector B has an angle of 46 degrees and a magnitude of 23. Remember, unless you use some tools, the angle and lengths of these vectors won't be accurate. So these pictures just help us see the vectors and which directions they're pointing. Now, let's use the tip-to-tail method to draw their resultant vector C. First, we draw A, and then we start B at the end of A. Then we draw vector C from the start of A to the end of B. If we want, now we can draw vector C at the origin to get an idea of its direction. However, if we didn't draw vectors A and B accurately, then C won't be accurate either. So we probably don't want to rely on this picture to determine its direction, and you can skip this if you want. But seeing vectors A and B added together visually is probably helpful. Okay, so what are the steps for adding two vectors? And what equations could we use to solve this? We learned that if we're adding vectors, we can find their individual components and then add those together to find the components of the resultant vector. Then we can use those to find its magnitude and angle. So if vector C equals vector A plus vector B, then the component Cx equals Ax plus Bx, and Cy equals Ay plus By. We know vectors A and B, we can find their components, then find Cx and Cy, and then use those to find vector C. We do need some other equations to work with vectors, like the trig functions, but these here will remind us of how to solve the problem. So first, let's find the components of vector A. Let's start by using the 122 degree angle that we're given. We learned that the x component, Ax, is equal to the magnitude, A, times the cosine of theta. We plug in 15 for A and 122 degrees for theta, and we get negative 7.95. Notice that the x component is negative because it points in the negative x direction, and plugging in this conventional angle takes care of the sign for us. Next, ay equals a times the sine of theta. We plug in the same values for a and theta, and we get 12.72. Let's save these components at the top. Another way we could have found the components is by using the reference angle. 180 degrees minus 122 degrees is 58 degrees, which is the angle between the vector and the x-axis. And if we draw out the components, it's the angle inside the triangle between the vector and the x component. If we plug in 58 degrees, then AY is still positive 12.72. But now AX is positive 7.95. That's just the length of the bottom side of this triangle. But like we said, AX points in the negative x direction. And since we're adding vectors, we need to include that negative sign for things to work out. Now let's find the components of vector b. Just like with vector a, bx equals b times the cosine of theta, and by equals b times the sine of theta. Now we plug in 23 for b and 46 degrees for theta, and we find that bx is 15.98 and by is 16.54. Let's also write those at the top. Now we can add the x components and the y components to find the components of vector c. Cx equals ax plus bx, which is negative 7.95 plus 15.98, which gives us 8.03. Notice that we're always adding the two components, but we can plug in negative values. Next, cy equals ay plus by, which is 12.72 plus 16.54, which gives us 29.26. Now that we have the components of vector c, we can find its magnitude and angle. We use the Pythagorean theorem to find the magnitude. If we rearrange that, then c equals the square root of cx squared plus cy squared. We plug in 8.03 for cx and 29.26 for cy, and we get 30.3 for the magnitude of vector c. To find the angle, we use the inverse tangent function, where theta is equal to the inverse tangent of the y component over the x component. When we plug in the values of cy and cx, we get 74.7 degrees for the angle theta. The angle we found is the reference angle between vector c and its x component, which is how the tangent function works. cy is the opposite side and cx is the adjacent side to this angle. But if the problem is asking us for a single value for the angle of vector c, we probably want to find its angle counterclockwise from the positive x-axis. So is that this angle or a different one? If we drew the vectors accurately, we would see the vector points in the positive x and positive y directions. But we don't need the picture to tell us that because cx and cy are both positive. So if this is the direction of vector c, then 74.7 degrees is the angle relative to the positive x-axis. If cx was negative, then the vector would point to the left, and we'd have to find 180 degrees minus the 74.7 degrees to find the conventional angle. So that's how we would solve this type of problem, which involves adding two vectors and using conventional angles relative to the positive x-axis. We had to really keep track of our angles and our positive and negative signs, but as we'll see, some vector problems are a lot simpler. So let's take a look at the next problem. A person is riding a zip line between two towers that are 185 meters apart. When they reach the end of the zip line, they are 20 meters lower than when they started. What is the angle of their displacement below the horizontal? Okay, so what information are we given here? A person is riding a zip line, and they have some displacement between the start and end points. Let's draw a dot for the starting point. The two towers are 185 meters apart, so let's draw a horizontal line labeled 185 meters. It also says the end point is 20 meters lower than the starting point, so let's draw a vertical line labeled 20 meters. Here's a second dot for the end point of the zip line. Now let's draw a displacement vector from the start point to the end point. We could have also labeled the distances like this. Since this question is talking about a physical scenario and it didn't mention anything about x and y axes, we're only dealing with positive, horizontal, and vertical distances. We can draw this picture however we want. We could even flip it so the displacement is going right to left, as long as the endpoint is 185 meters from the start in the horizontal direction and 20 meters down in the vertical direction. If you want, you could also draw the towers and the ground, but we'll just use this picture. So the question is asking us to find the angle of the displacement below the horizontal, which means the angle between the vector and a horizontal line. In the picture, that's this angle. For the given information, it probably makes more sense to just reference the labels in the picture instead of writing out the information in words. But we could write that we're trying to find theta, which is the angle. So how would we find theta? Well, from our picture, we can see the displacement and the two distances form a right triangle. So we can just use the inverse tangent function to find theta. The opposite side from the angle is 20 meters, and the adjacent side is 185 meters. If we plug that in, we find that theta equals 6.2 degrees. So we'd say the displacement is 6.2 degrees below the horizontal. And that's it. For problems like this, where we're given some distances or lengths, we just have to draw what the physical scenario might look like and use geometry to find what we're looking for. If you want, you could include the x and y axes and say that the x component of the displacement is 185 meters and the y component is 20 meters, but it's not always necessary. In this case, we're just dealing with positive distances and angles, so using geometry is enough to answer this question. Now let's take a look at the next problem. A plane is flying 800 kilometers per hour south with no wind. Over a short period of time, a strong wind develops with a speed of 120 kilometers per hour in the west direction, causing the plane to drift off course. Assuming the pilot doesn't make any changes, what is the new speed of the plane over ground, and what is the angle between the plane's original direction and its new direction due to the wind? Alright, there's a lot of information there. Let's read it again and pick out what's important. A plane is flying 800 kilometers per hour south, with no wind. So we have a plane with a velocity vector, and the plane has that velocity without any wind. Over a short period of time, a strong wind develops with a speed of 120 kilometers per hour in the west direction. So now we also have some wind which has its own velocity vector of 120 kilometers per hour west. This causes the plane to drift off course, so the direction of its motion changes. The pilot doesn't make any changes, which means the plane doesn't speed up or slow down, and it doesn't turn to compensate for the wind or anything like that. The problem is asking us to find the new speed of the plane over ground and the angle between the plane's original direction and its new direction. So if we're looking for the new speed of the plane and its new angle, That means we're looking for the magnitude and angle of the plane's new velocity vector. Let's draw some things to help us solve this. First, we're dealing with compass directions, so let's draw those for reference. The plane starts with a velocity vector of 800 kilometers per hour south, so let's draw that and label it as VI for the initial velocity of the plane. Then, later on, we have some wind with a velocity of 120 kilometers per hour west. The plane is still flying 800 kilometers per hour south through the air, but the air happens to be moving west at 120 kilometers per hour. So, relative to the ground, the plane has a new velocity vector, which is its original velocity vector plus the velocity vector of the wind. Let's label this new velocity as VF for final velocity. This is like a boat pointing straight across a river, but there's current pushing the boat sideways, so the boat moves at an angle. Don't worry if this scenario isn't intuitive. It should make more sense after practicing these types of problems, and we'll explain this stuff more in the lesson on relative motion. But for this problem, we want to find the magnitude of VF and its angle relative to VI, the original velocity vector. For the given information, we can write down that for the plane, VI is 800 kilometers per hour south, and for the wind, its velocity is 120 kilometers per hour west. But like last time, it might just be easier to label the pictures. And we're trying to find VF, the magnitude of the new velocity vector, and theta, the angle between VF and VI. So we're adding two vectors, but since they're perpendicular to each other, they already form the components of the resultant velocity vector. So all we need to do is find the magnitude and angle of the new vector, and we can use these equations. First, let's find the magnitude. If we rearrange the Pythagorean theorem equation, the magnitude of VF is the hypotenuse, C, and A and B are the legs of the triangle, which would be 800 kilometers per hour and 120 kilometers per hour. When we calculate that, we get 809 kilometers per hour for the magnitude of VF. Now let's find this angle. In this case, the opposite side from the angle is 120 kilometers per hour, and the adjacent side is 800 kilometers per hour. When we plug those in, we get 8.5 degrees for theta. So the new speed of the plane over ground is 809 kilometers per hour, and the angle between the plane's original direction and its new direction is 8.5 degrees. For this problem, we used compass directions, and we didn't use the x and y axes. We added one-dimensional vectors and found a reference angle. But if the problem was asking us to add two-dimensional vectors, like in the first problem, then we would have to keep track of positive and negative components, and in that case, it might make sense to use the x and y directions to keep track of things. Alright, let's move on to the last problem. A hockey team is practicing on a rink with an imaginary x and y coordinate system in units of meters. A puck is sitting at coordinates 6, 4 when player A passes it across the ice to player B. The puck moves at a constant velocity of 16 meters per second, assuming no friction, at an angle of 72 degrees relative to the x-axis. What are the coordinates of player B if they receive the puck in 2 seconds? So what's happening in this problem? We're working with coordinates, a velocity vector, and there's time involved. We have a hockey puck that starts at some initial position, then it moves with a constant velocity vector for a period of time, and ends up at a final position. Let's read through this again, draw a picture, and write down the important information. A hockey team is practicing on a rink with an imaginary x and y coordinate system in units of meters. So the problem is talking about a real-world scenario, but we're going to describe things as if they're happening on an x and y coordinate system. Let's draw the x and y axes to start the picture. Next, a puck is sitting at coordinates 6, 4. Let's draw a dot to represent the puck and label its coordinates. Since the coordinates are in meters, we can write down that the initial x position is 6 meters, and the initial y position is 4 meters. Player A passes it across the ice to player B. The puck moves at a constant velocity of 16 meters per second at an angle of 72 degrees relative to the x-axis. So let's draw the velocity vector of the puck and write down the magnitude, v, is 16 meters per second, and the angle, theta, is 72 degrees. The problem is asking us to find the coordinates of player B, who receives the puck in 2 seconds. So the problem is basically saying if the puck has this initial position, then moves at this velocity, what's the position of the puck after 2 seconds? So let's draw a second dot for the final position of the puck, where player B is, and write down that we're trying to find its coordinates, x final and y final. Since we're working with vectors, we need the usual equations to find the components, or the magnitude and angle. But since this problem involves velocity, time, and initial and final positions, let's write down these two equations for displacement and velocity. They both use x, but we know the equations are the same for the y direction. We know the initial positions, the velocity, and the time, so we can find the displacements and the final positions. So before we dive in, let's talk through how we could solve this. One way is to use the velocity to find the displacement vector of the puck during those 2 seconds, and then find the x and y displacements, which we can add to the puck's initial positions to find the final positions. Another way is to find the x and y velocity components and use those to find the x and y displacements, and then add those to the initial positions. Let's try both ways to see what they look like. First, let's find the displacement vector and then find the components of the displacement. The puck is moving 16 meters per second in a straight line at 72 degrees. So after 2 seconds, the puck will move some distance in that same direction. So the displacement vector will have the same angle as the velocity vector. But what's the magnitude of the displacement? Since we're only looking at the motion in a straight line, we can treat it as a linear motion problem. Velocity equals the displacement divided by the period of time. Instead of delta x, let's use d for the magnitude of the displacement in the direction it's moving. So v equals d divided by time. We can rearrange that to isolate d on the left, and then plug in 16 meters per second for v and 2 seconds for delta t. That gives us 32 meters for the displacement. That's pretty simple math. The puck moves 16 meters per second for 2 seconds, so it travels 32 meters in that direction. Now that we have d, we can find the x and y components, how far the puck moved in the x and y directions. Using the trig functions, delta x equals d times the cosine of theta, and delta y equals d times the sine of theta. We plug in 32 meters for d and 72 degrees for theta. That gives us 9.9 meters for delta x and 30.4 meters for delta y. Now we can find the final positions of the puck. Delta x and delta y equal the final positions minus the initial positions. We can rearrange those to isolate the final positions, which means we're just adding the initial position plus the displacement. We plug in 6 meters for x initial and 9.9 meters for delta x to get 15.9 meters for x final. Then we can plug in 4 meters for y initial and 30.4 meters for delta y to get 34.4 meters for y final. Putting those together as coordinates, the final position of the puck would be 15.9, 34.4. Now let's look at the other way to solve this problem. First, we'll find the x and y velocity components. Then we'll use those to find delta x and delta y. So the x component, Vx, would be v times the cosine of theta, and Vy is v times the sine of theta. We plug in 16 meters per second for v and 72 degrees for theta, and we get 4.94 meters per second for Vx and 15.22 meters per second for Vy. So as the puck moves from the initial point to the final point, it moves to the right at 4.94 meters per second and moves up at 15.22 meters per second. Now we can use those to find delta x and delta y. We could use these two equations and solve this in 2 steps, but if we take the equation for velocity and replace delta x with x final minus x initial, and then we rearrange things, we get this equation, and we can calculate the final positions in 1 step. We plug in 6 meters for x initial, 4.94 meters per second for Vx, and 2 seconds for t. That gives us 15.9 meters for x final. For the y position, we plug in 4 meters for y initial, 15.22 meters per second for Vy, and 2 seconds for t. That gives us 34.4 meters for y final. That's the same answer we got before. We just did the steps in a different order. So that's an example of a problem that combines coordinates, vectors, and some kinematic equations. Alright, that's it for this video. Thanks for watching, and I'll see you in the next one.